Welcome all for the lecture of complex analysis 5. In the previous classes, we started with a complex integration. In the complex integration, we started with basic integration related with real as well as complex integration, line integration, as well as some Cauchy's theorem for the complex analysis. Now we will discuss starts with the Cauchy's theorem. There is a continuation, that is an extension version also. We are starting here. You know that integral upon c f of z dz is equal to 0 is a Cauchy's theorem. Here f of z is an analytic function inside a closed disk c into dz is equal to 0. This implies that the line integral between any two points is independent of the path as long as the function is analytic in the region enclosed by the path. Here you can see the R simply connected region here. If you are observing here, there are 2 points inside the region. Then in that there is a lines, that is line integral. One of them is C2, another one is C1. Then here integral upon, because it is a closed curve, then that can be written as integral upon C f of z dz can be expressed as, because from A to B and B to A. Then if it is a line integral, integral upon A to B f of z dz is equal to minus time integral upon B to A. If you interchange the limits, then it becomes negative. Similar way here, integral upon c1 f of z dz is equal to integral upon c2 f of z dz. Using this concept, we can make the line integral between any 2 points is independent of the path as long as the function is analytic in the region enclosed by the path. It is a simply connected region. Here you can see C to C, that is a closed, then it can be interrelated. Extension of Cauchy's theorem to multi-connected region. Here you can see this is our multi-connected region. Here C1, C2, here another one is there, and this can be made it into a, here we can make a cut for this, then that can be transformed to a closed region. You can see, observe. Here it is starts from C2, then this becomes C1, then again here C1, again here this is capital C1. This is capital C1 and C2. Then here we make a cut, that is small c1, another one is C2. There is a connection from here to there. R dash is a simply connected region. If f of z is analytic in R, the region, then integral upon C of C1, C2, f of z dz not equal to 0 in general. Introduce an infinitesimal width bridge to take, this is a bridge we made, R into a simply connected region R dash, then integral upon C, C1 minus C2 plus C1 plus C2, that is it cancel each other because what direction is different. Then f of z dz is equal to integral upon C1 f of z dz minus integral upon C2 f of z dz is equal to 0, since integral along C1 and C2 are the opposite direction. Here you can see that 2 become cancelled. Thus integral upon capital C1 f of z dz is equal to integral upon C2 f of z dz. Unlike in Cauchy's theorem, now integrals are usually non-vanishing. Now we again revisited to Cauchy's theorem. If a function happens to be analytic everywhere within a simply connected region, then we can shrink the closed path. Here, this can be shrink to a closed down to the zero size, where verifying that the line integral around the closed path must be 0. Here, this is the path. It is shrink to a small, that is r dash. We can, this is r dash, that shrink into a simply connected region. This is the diagram. First we can make to shrink this one, we get this one. That is a shrinking path down. Fundamental theorem of calculus of variable. This is an extension of the same theorem in calculus for real function to the complex function. We already discussed whenever I discussed in the line integral that is the same thing here also. Suppose we can find capital F dash such that f dash z is equal to the derivative of f divided by dz is equal to small f of z. If we take integral upon ZA2, here we can make ZA to ZB, f of z dz means integral upon small f of z is same as capital, that's d of derivative of capital F divided by dz into dz, then that become the functional values f of zb minus f of za. That is a fundamental theme of a calculus in real function that is extended. Here, the integral is a path independent. We already observed in the previous slides. If f of z is analytic on paths from za to zb, starting some assumption that if integral upon za to zb, f of z dz is a path independent, is simply connected, or true if f is an analytic in the region R. Then integral upon za to zb, f of z dz is equivalent to a, because you know that integration is a limit of a sum. Here the limit of n tending to infinity, summation n running from small 1 to capital N. Here 1 to n capital N, that is f of n into delta Zn. Delta Zn is the length, each interval length Zn to Zn minus 1. Then Zn is a curve between Zn minus 1 to Zn. Suppose we can find f of z such that f dash z is equal to df by dz is equal to small f of z. Hence, f of n can equivalence to cap delta fn divided by delta zn. That is the f of functional f of zn minus f of zn minus 1 divided by delta zn. That is the rule of derivative of that function. The definition limit of z delta zn tends to 0. Here, integral upon za to zb, f of z dz is equal to limit of some limit of delta zn tends to 0. Summation from n1 to capital N is f of zn into delta zn. Here, f of zn is equivalence to, we can rearrange this into delta fn divided by delta zn. That is small change. These two become cancelled to each other. Then here delta fn starts from 1 to capital N. If you make a expanded version of this delta fn, then that becomes f of z1 minus f of za plus f of z2 minus f of z1 and f z naught. This is f of z naught, f of z3 minus f of z2, etc. Here previous term is cancelled with this, and this 2 is subtracted, and these 3 become subtracted to each other. Then finally your remaining is f of za plus f of zb, means that is f of zb minus f of za is that is a fundamental rule, that is path independent if f of z is analytic on the paths from za to zb. Now we will discuss about the Cauchy's integral formula. Here this is a simply R is a simply connected region, and this is a, we make into a R simply connected region, that is R dash, we make it into R dash is simply connected region. We draw here and make it into a circle center Z naught and point Z naught, and C naught is the another circle we join here. That is the things. Here f of z is assumed analytic in R, but we multiply a factor 1 by z minus z naught. Here z minus z naught is a polynomial function. It is analytic except it is not analytic at z naught. That is analytic except at the point z naught, and consider the following integral around C, that is a contour integral upon C, f of z divided by z minus z naught into dz. Here to evaluate this, consider the paths capital C. here capital C plus small c1, and this is another part c2, then another C C naught, C1 and C2 shown that enclose a simply connected region for which the integrand is analytic and on and inside the path. And also we already observed that the independent paths, one direction is different from the another. Then C1 and integral upon C1 and integral upon C2 f of z dz become same, then these two become cancelled to each other, that becomes 0, then remaining is integral upon c plus integral upon c naught. F of z dz is equal to z minus z naught dz is equal to 0. This implies if you transfer that, that become minus sign, minus of f of z divided by z minus z naught. Here this is a circle equation c naught. It is known that z minus z naught is equal to r e power I theta, then we can utilize that formula. Here we can draw and close a circle z naught, and z is c naught is a point, then z minus z naught is a r e power I theta equation of a circle. If you use this equation of a circle and then differentiate with respect to z, then dz is equal to, because z naught is a point, it's a constant number, that become 0. Then r into e power I theta, if you differentiate with respect to theta, e power I theta is I into e power I theta into d theta. Then these things can be substituted in this function, because around c naught, then integral upon c naught f of z divided by z minus z naught into dz is equal to f of z naught. Then it is a circle 2 pi to 0 or 0 to 2 pi r into r I e power I theta into d theta, r into, because z minus z naught is r e power I theta. You can substitute this function here, then this become r into e power I theta, then dz become r I e power, these two become cancel to each other, remaining is I into d theta. I into d theta means you get theta, theta means you can apply the limits, then minus into minus, that become plus 2 pi I into f of z naught. If r is a tending to 0, then integral upon c f of z divided by z minus z naught into dz become 2 pi I into f of z naught. This is known as Cauchy's integral formula. Here f of z is an analytic function, z naught is an another point lying inside the circle mod z minus z naught is equal to r. Then this f of z naught is equal to, and z naught is a neighborhood of a point z, then f of z naught is equal to 1 by 2 pi I integral upon c contour integration f of z divided by z minus z naught into dz is known as Cauchy's integral formula. This can also be rearranged. You get 2 pi I into f of z naught is equal to integral upon c f of z divided by z minus z naught into dz. We must note here the value of z naught, f of z at z naught is a completely determined by its value of c. If it is outside, then the value become 0. It is only inside the region. Note that z naught is outside C. The integrand is analytic inside C. Hence, Cauchy's theorem we have integral upon 1 by 2 pi I integral upon C f of z divided by z minus z naught dz is equal to 0. In this, we must remember some of the application. Here, integral upon c f of z dz divided by z minus z naught dz is equal to 2 pi I into f of z naught if z naught is a inside c. If it is outside, the value become 0. In a graphical displays, one often wishes to determine if a point z naught is in the ordered pair x comma y is hidden by a region with a boundary c. In front of it, that is, if it is a 2D projection, Z naught appears to fall inside or outside the region. Just choose f of z is equal to 1. Some of the examples related to evaluate the integral. Here, Integral upon C, f of z is 1 by z plus 2 into dz, and C is equal to, this is the region, it is a unit circle over unit circle is centered at the origin, and z is equal to minus 2. Here C is minus 2. Then z plus 2 to the power of minus 2 is analytic inside C. First, we can check in the denominator what are the points. Here z is equal to 0 is one point, z is equal to minus 2 is the another point. Here z is equal to 0 is only the point inside the region, another one is outside the region. That's why here choose here the function f of z become 1 by z plus 2, that is inside. Then 1 by z is equal to, it is outside that point, then we can make 1 by z minus 0. 0 is a point, then we can apply here, that is 2 pi I into, you can apply z is equal to 0 here, then you get 1 by 2. Then we get pi I. Alternatively, we can make this problem can, because if you see, because only one point is outside, that's why we chosen f of z is analytic function, because 1 by z plus 2, because z plus 2 z plus 2 is a polynomial function, it is analytic everywhere, but here the region is given, it is always inside, but it's outside the function, that's why we chosen that point. Otherwise, we can make using partial fraction for this, and this can be written as a by z plus b by z plus 2. Then we can find the values for a and b. We get 1 by 2 times 1 by z minus 1 by z plus 2. Then we get two integral, Cauchy's evaluation of the contour integral, 1 by z dz, integral upon dz by c into 1 by z plus 2. Then here it is inside c, then this become 1 by 2 into 2 pi I. Then this value, because outside the region, this is 0, this is 2 pi I. Then simplify, you get same solution. Then integral with two singular factors. Here integral upon C 1 by z square minus 1. It is an unit circle centered at the origin is given. Here first you can solve this one. 4z square minus 1 is equal to 0 means z square is equal to 1 by 4. Z is equal to plus or minus 1 by 2. Z is equal to plus or minus 1 by 2 means this is the unit circle centered at the origin, and 1 is the radius here, and minus of and plus of are lying here. You see, these are the 2 points inside the region. Then first you can simplify this in terms of 1 by z square minus 1 is 1 by 2z plus 1 into 2z minus 1. Then using partial fraction, you know that we can simplify this 1 by 2 times 1 by 2z minus 1, 1 by 2z plus 1. Then these are the points z minus 1 by 2 minus 1 by z plus 2. Then apply the contour integration. You know that it is 2 pi I. This is also 2 pi I. And 1 minus 1 is 0. 2 pi I is a common. We can take outside. And 1 minus 1 is 0 is the solution for this problem. Now we can extended version of a Cauchy's formula, that is known as Cauchy's derivative formula. Here, since f of z is an analytic inside the region, its derivative exists. Let us express in terms of Cauchy's formula first. That is f of z naught is equal to 1 by 2 pi I f of z divided by z minus z naught into dz. Here that you know that f of, if you make an increment for this z naught, then that becomes z naught plus delta z. Here also z naught changes to delta z. Here also these two z naught changes to z naught plus delta z. Here z naught changes to minus z naught minus delta z. Then we can subtract this, that is f of z naught plus, we call that as equation 1. This is equation 2 means 2 minus 1 by delta z means this become f of z naught plus delta z minus f of z divided by delta z, then that is equal to 1 by 2 pi I into delta z, then the integration, and because we can make minus of this, because this also analytic, this is also analytic, then the change, if you make a f of z is a common factor, take LCM to each other and rearrange, this become f of z, delta z will be remain, then these two become cancelled to each other, then f of z naught plus delta z minus f of z divided by delta z, limit of delta z tends to 0 means we get z minus z naught here, here also z minus z naught, this becomes 0, and 2 times of z minus z naught means z minus z naught the whole square into dz. This is the derivative, the fundamental definition of the derivative, that is f dash z naught. We have also just proven we differentiate with z naught under the integral side. Here, instead of doing this, we can use Leibniz rule for integration. Then what happens, there's this function f dash z naught, then 1 by 2 pi I, this is 1 by z minus z naught, is a function, because we are derivative with respect to z naught, means this is minus 1 by z derivative is minus 1 by z minus z naught, the 1 by z, derivative of 1 by z is minus 1 by z square. Similar way, here this function 1 by z minus z naught the whole square minus 1 by z minus z naught the whole square. Then inner function, but because it is a chain rule, if you differentiate inside, this becomes 0, this become minus 1. Minus into minus become plus, you get 1 into f of z divided by z minus z naught the whole square. If you extend this one, the second derivative, that is f double dash z naught is equal to, that become here minus 1 by z minus z naught the whole cube into again minus minus become plus, and 1 into 2 will be there. 1 into 2 means that is 2 factorial. Means second derivative become 2 factorial divided by 2 pi I integral upon c f of z divided by z minus z naught the whole cube. In general, we can write fn of z naught is equal to n factorial divided by 2 pi I into integral upon c f of z divided by z minus z naught to the power of n plus 1 into dz. That is the general derivative formula of a Cauchy's integral. That is the thing we discussed here. This is f dash f double dash z naught is 2 by 2 pi I integral upon c f of z divided by z minus z naught the whole cube into dz. In general, we can make it into fn of z naught is equal to n factorial divided by 2 pi I integral upon c f of z divided by z minus z naught to the power of n plus 1 into dz. You must remember this. It is one of the important theorem, Cauchy's integral formula. F of z is a analytic in simply connected region containing C here. You must remember this. If f of z is analytic in C, then its derivative of all orders exist, and also they are also analytic. You must remember. Note that f of z and all its derivative can be determined from the boundary values. These must be, you must remember. We will give some examples related to these concepts. This is the theorem you must remember. We can make it into fn z naught by n factorial into 2 pi I. That also we can remember. This is a function, you know that sine f, here f of z is, if you're comparing this, f of z is sine square z, sine square is analytic function or trigonometric function, then f third derivative, if you comparing this is f3 of a is here, z naught is a, 3 factorial divided by 2 pi I integral upon z naught sine square z divided by a, here n is equal to 3. Then you can derive derivative of 3. Third derivative is needed here. That's why first derivative become 2 sine z into cos z, that is sine 2z also. Or you can make Directly, f third second derivative 2 times cos square z minus sin square z, and f third derivative is minus 8 sin z into cos z. Here also we can make sin 2z, then cos 2z, then again 2 into 4 into cos z. That is a derivative. If you make a simplification also, you can make another way. F3 of z, you put a, then I is equal to 2 pi I into 3 factorial into f3 of a, here minus sine 8 pi I into sine a into cos a. We can make this 2 sine a cos a sine 2a. We can rearrange that also in the form of minus 4 pi by 3 into sine 2a. Now that is a Morera's theorem. It is known as converse of Cauchy's theorem. What is converse of a Cauchy's theorem? A theorem, what is Cauchy's theorem? A function f of z is analytic function inside a closed region or simply connected region, or then integral upon c f of z dz is equal to 0 is a Cauchy's theorem. Here, Morera's theorem is a converse of Cauchy, means if a function f of z is continuous in a simply connected region R, and integral upon c f of z dz is equal to 0, means for a very closed contour C within R, then the function must be analytic throughout R. That is the converse. Here capital F will be analytic if we can prove its derivative exists. Let us consider the contour integration. This is given. This is given that integral upon c f of z dz is equal to 0. Means, what is the meaning of this? Here, the function f of z is an independent path. So that we can express in terms of capital F of z is equivalent to integral upon z naught to z and f of z into dz. Note that f of z minus f of z naught is equal to capital F of z, that is equal to integral upon z naught to z f of z dz. And also f of capital F of z minus f of z naught divided by z minus z naught is equal to integral upon z naught to z f of, means here dividing this by z minus z naught, then we get this one. We can choose a small straight line path here between 2 points, since the integration is independent, path is independent. Then this become, it is changes to f of z naught divided by z naught. It is also a path, dz is a path, then z minus z naught, that is equal to f of z naught, because the function is continuity. If it is a continuous function, f is a continuous, then this become f, the limit exists at that point, then it is continuous. This is the definition, because limit of delta z tending to z naught means this function become derivative. Derivative means the function is, each and every point is an derivative exists, means it is a analytic function. Therefore, this f is analytic at z naught in R, but then so all its derivatives, including capital F dash is equal to small f. Hence, f is analytic at z naught. I already discussed this. There is a, both are converse to each other. That is Cauchy's theorem statement. If f of z is analytic in a simply connected region R, then integral upon c f of z dz is equal to 0 inside the C in R. What is Morera's theorem? If a function f of z is continuous in a simply connected region R and integral upon c f of z dz is equal to 0 for a very closed contour C within R, then f of z is analytic throughout R, means these two are converse of one another. Now we will discuss this diagram tells us the properties of analytic function. Here you can see Cauchy Riemann equation, means that is an analytic. means it is the existence of derivative of all order, means that is a path of independent. If it is a path of independent, means integral upon cf of z dz is equal to 0. Then existence of f dash z, that is existence of f dash z, means that is a Cauchy's condition. These are the properties of an analytic function. Now we will discuss two important theorems. That is, one is Cauchy's inequality, another one is Liouville's theorem. Suppose f of z is an analytic inside a region, and also it is bounded analytic function, and it is convergent to a power series x representation. F of z is equal to summation of n 0 to n infinity an into z power n within a circle of radius r about the origin. Then mod an, suppose if you take any point inside, that's mod an is less than or equal to m divided by r power n. Here consider the following integral. You know that 1 by 2 pi I f of z divided by, because we taken it is from the origin, z naught is 0, z minus z naught to the power of m plus 1. That becomes z to the power of m plus 1 into dz. Mod z is equal to capital R, the radius capital R. Then this become 1 by 2 pi I, and also integration is a limit of a sum, that is summation n running from 0 to infinity an into integral upon mod, sorry, we can substitute here f of z is equal to summation of n 0 to infinity an integral upon mod z to r z to the power of n minus m minus 1, because here z power n is there, here z to the power of m plus 1. If you rearrange using line integral example, n minus m minus 1 is minus 1, that is minus 1 means this become an independent path, that is 1 by z. You get dz, that is circle 1 by 2 pi and 2 pi I into am. Am and an are the same. Then mod am is equal to 1 by 2 pi I, sorry, 1 by 2 pi, because if you put a modulus, integral upon mod z is equal to r f of z divided by z power m plus 1 dz. If you substituting here, that is 1 by 2 pi I, sorry, 2 pi integral upon mod z is equal to r. If you take a modulus inside, that becomes less than or equal to inequality. Mod ab, or mod a by b is less than or equal to mod a by mod b. That is, if you integrate each integral, then this is less than or equal to 1 by 2 pi integral upon 0 to 2 pi, because it is a circle centered, and it starts from 0 to 2 pi, and m mod f is a bounded, that is bounded to m by an is bounded to rn, then m divided by r to the power of m into r d theta. Then rr become cancelled, then m by r power n are m, both are same because independent. If m tends to n, then mod an is less than or equal to capital M divided by r power n. Here m is the maximum of mod f of z, mod z is equal to r. This is the Cauchy's inequality. Then if a function, and also we note that here, if a function is analytic within a circle, then it must have a convergent power series expansion within C. You already learned in your real analysis, that is Taylor's theorem. Here also we will extend to the Cauchy's in the next parts. Now we will discuss the Liouville's theorem. What is Liouville's theorem? This is one of the important concepts you must remember. A function is analytic and bounded in an entire complex plane, or analytic in a complex plane, and then it is constant. The function itself a constant. Here, before proving the Liouville's theorem, we must remember bounded and also in the Cauchy's inequality properties, we must remember, then it is a very simple theorem. By the Cauchy inequality, mod an is less than or equal to m by r power n for any r. So let us r tends to infinity, because it is a series expansion. F of z is equal to summation n 0 to infinity an into z power n. Here an is equal to 0 means n is not equal to 0. The function must be equal to a naught. No interesting, that is a non-constant function f of z is analytic and bounded everywhere. Therefore, z power n is analytic everywhere but unbounded at infinity. 1 by z minus z naught to the power is not analytic at z is equal to z naught, and some examples, that is sin z, e power z, are analytic everywhere but it is unbounded at z is equal to infinity. Minus z to the power of 1 by 2 is analytic except at the branch z is equal to 0 and along a branch cut. Here we must remember any function f of z is analytic, unbounded in an entire function means it must be a constant. Here, to analyze f of z at z is equal to infinity, we can set z is equal to 1 by xi and examine the behavior of f of 1 by xi at xi is equal to 0. Here, we will discuss the Taylor series. Here, f of z is equal to 1 by 2 pi I integral upon c dz. Here you can take a circle center c of z dash. Here z1, z0, z. Here we can draw. Here 1 by z naught z dash to z is equal to 1 by z dash to z naught minus z minus z. Z can be taken as here adding and subtracting z naught here in this. Then we can rearrange this. Then this become 1 minus, if you take common factor means that is 1 minus z naught divided by z dash minus z naught whole power minus 1. Means here 1 by 1 minus x form, you must remember. Then this is 1 by 1 minus x means that is 1 minus, that is directly we can write summation x power n using same what we done in a real analysis. That factor, that form 1 by 1 by 1 minus x is a geometric series that can be expressed. That is 1 minus z naught to the by z dash minus z naught. Then 1 by z dash minus z naught means this is the power of n summation n 0 to infinity, that is z minus z naught divided z dash minus z naught to the power of n means we can make it into here term, we can term inside, then f of z is equal to 1 by 2 pi I summation n 0 to infinity z minus z naught to the power of n is a constant we can take outside, integral upon c that z dash means f of z dash divided by z dash minus z to the power of n plus 1. Here this is known as positive terms of the series. We can make this function z minus z naught to the power of n into n factorial into, this is the derivative of a Cauchy's nth derivative formula Fn of z naught. Let z1 is a closed singularity from z naught, then this z1 and z dash that we have made here z naught and z1, z naught is closest singularity from z naught, then the radius of convergence is z1 minus z naught. That series converges for mod z minus z naught is less than mod z1 minus z naught. And Laurent series, it is a combination of positive as well as negative series, and also it is in an annular region. Here let f be a analytic within the annular regions, that is small r and capital R. Here this is radius r and another radius is capital R. R is lying between z0 and z. Here mod z minus z0 is less than or equal to capital R and less than or equal to small r. And then this function f of z is 1 by 2 pi I integral upon c1 minus integral upon c2 dz dash into f of z dash, here z dash and z dash c1 and c2 annular region. Here that is c1 is a, this is first one up 1 minus z naught, z dash minus z, and here another one we can make positive exactly same way what we done in the Taylor series. Similarly, C2 become Z dash minus Z, then that is 1 minus 1 by Z minus Z naught Z, you get a positive as well as negative series. Then the combination of these two, we get a Laurent series. F of Z is equal to 1 by 2 pi I into summation n 0 to infinity Z minus Z naught to the power of n integral upon Cz dz dash f of Z dash divided by Z dash minus Z naught to the power of n plus 1, another one plus 1 by 2 pi I summation rest 1 by Z minus Z naught to the power of n plus 1 into this one. Then finally, that f of z can be expressed in this form. Then that is, one is the positive starts from 0 to infinity, another one is minus infinity to 1. If you combining this, we get f of z is equal to nz minus infinity to infinity an into z minus z naught to the power of n. This is known as Laurent series. Combine the both positive as well as negative terms. Then here an is the where an is 1 by 2 pi I integral upon c f of z dash divided by z dash minus z naught to the power of n plus 1 into dz naught. C within F region of analyticity. We will give some examples related to Laurent expansion. Let us start examples of Laurent expansion. You know that Laurent expansion f of z is equal to summation n from minus infinity to infinity an into z minus z naught to the power of n, where an is the 1 by 2 pi I integral upon c f of z dash divided by z dash minus z naught to the power of n plus 1 into z dash. Let us consider the first example. F of z is equal to 1 by z minus z naught. Consider the expansion z naught is equal to 0. F is analytic at the region mod z is lying from 0 to 1. Here from the binomial expansion, or first we can make this function in the form of using direct method, or we can use the partial fraction method. Find it is in 1 by z minus 1. It is a linear expansion. We can take it as a by z plus b by z minus 1 here. Then find a and b, combination of this. Then you get f of z is equal to minus 1 by z plus 1 by z minus 1. Because here it is mod z is less than 1. Here mod z is less than 1 means 1 minus 1 by z as it is. Here this is, we can rearrange this. 1 by 1 minus x. 1 by 1 minus x is a series, that is summation n from 0 to infinity z power n. Directly we can write. Then we can substitute by using Laurent series. An is equal to 1 by 2 pi I integral upon dz 1 by z to the power of n plus 1 z into z minus 1 is equal to minus 1 by 2 pi I summation k from 0 minus infinity integral upon c dz z to the power of k divided by z to the power of n plus 2. Minus 1 if n is greater than or equal to minus 1, 0 otherwise. We can represent this function in terms of minus n running from minus 1 to infinity z power n, because this also include, then this become, it is start from 0. If it taken inside, that becomes z to the power of minus 1, means that is 1 by z. For this, we can refer, these are the following books for basic complex analysis. That is, yes, Ponoswamy is a foundation of complex analysis, and Alpher's complex analysis, McGraw-Hill, and some of the examples related to complex variables. We can refer Sham series outline, and also some of the important advanced things for complex variable and applications. We can study J.M. Brown and Churchill. Thank you.